Check. Check.
Check.
Okay, there we go.
Check.
I think we are good. Okay, I'm gonna do some more distortion implementation from the same paper that we looked at Monday. I'm gonna do a tube distortion this time, and I want to start organizing this stuff better. I have this folder called modules. I don't really know if I like that name, but I need a way to differentiate between like small, like single responsibility type things, like just the wave shaper, as opposed to a module that has like multiple instances of other things. So I think I might leave the name modules for the smaller things. And then for these, like the master bus and the console, that's gonna have to have a different name. Maybe like something to the effect of like a rack or like a rack unit. How about unit? Let's just do that. Units. Oh, that's not how you spell that. Okay. And I'm gonna, let's see, can I do it from here? Take the master bus, put it in there. Yep. And then the console. Yep. Okay. And where are we right here? Let's see. Process block. I'm going to get rid of these two. And since we are kind of just experimenting, I think I'm going to go back and put my gain to be 0 to 100 and then just kind of scale it inside of each module as we need. Okay, let's see. Can we build? Also, I added some build instructions and repo cloning instructions to the README. So if you haven't tried to clone it yet, you can try now. And if there's any issues, you can let me know. Okay, cool. Good. All right, so let's start with some tube stuff. Let's make a new file. We're just gonna call this tube. Don't need any of that nonsense. And let's see here, process block. Let's go grab that. What we got? It's called modules. Tube. Good. All right. And we can take kind of the same stuff from here. Like let's just take the whole thing. Okay. Oh, somebody just joined the Discord. All right, tube, drive smoothers. Yep, don't need this though. Process block, sure. Set drive, sure, but we don't need these two. And we don't need these for now. I guess we are going to use something similar, but one thing at a time. Okay, Charlotte, so I will show you the pages from that Will Perkle addendum. And this one's even easier because he has actual code. He also gives you kind of an overview of the signal flow. So it's got this clipper compressor. It's got this DC integrator. It's got a nonlinear wave shaper, low shelf, DC blocking filter, this high filter, and some amplification and stuff. But that's all, that's all pretty standard. Some of the stuff like I implemented this already just to test this out. I don't think the low shelf is even necessary. It seems fine. Also, in his code, he doesn't necessarily use the lossy integrator thing, so just skipped over that, and I mean, it seems fine. Let's just go over to what it's supposed to look like. Where we at? He also has this. It kind of shows you the natural compression that the tube gives. Oh, and that's something I didn't think to check in plugin doctor. Well, after we implement it, let's check that too to see if it matches up. So where is our oscilloscope view? Here we go. Perfect. This is what we're looking for. This is the typical tube shape right here. All right. So let's just dive in. It's only really two methods. And then a couple of filtering things. So we've got this valve grid conduction and then the actual valve emulation. And then after we do this tube, there's some stuff about it that I like and I think we can reuse to make an overdrive that sounds really good. So yeah, let's get us a nice inline float process. What was it called again? Just call it conduction. And we also process. I'm just gonna call it process tube. Okay, awesome. We need some variables in these. Let's see, what do we need for the grid conduction again? We got, just the input and a threshold. Okay. So let's do const float xn const float thresh. And the good thing is that Will Perkle already found the best values for each of these. So yeah, we can just go ahead and copy this. All right, cool. We'll do a little optimization after. We'll measure the performance and stuff, but I'm just going to do the if statement first. We do something, and then else we return the input. Okay, what do we got here? What do we got to do? We got to call something clip delta. All right, so let's do that. Xn minus thresh, I think it said. Oh, but not const. Okay. Then we'll say clip delta. F max. Yeah, okay. Equal to SDD F max. That clip delta and 0. And then we got this compression factor thing. Let me grab that. const float. And this right here, a tiny little optimization we can do is we don't actually need to calculate this in the sample loop. It is just an addition, but why do it? Static const expr float. I'm just gonna call it, I don't even remember what it was called. I'm just gonna say compression term. Make sure they're floats. And then we could drop it in right here. Let's also make sure we're calling stdexp. Okay, what doesn't it like? Nope. Float. Oh, yeah, okay. Right there. It did not like that it was float and double. All right, that. And okay. Return compression factor times xn. And that takes care of the compression part of the tube in this diagram up here. Let's see where we at. Yeah, the clipper compressor. Okay. All right, let's do the actual tube part. Now this one's long and it's got a bunch of if statements. And I actually already tried it out and I tried to optimize it with that mask pattern and it actually made it slower. So I guess whenever there's a bunch of if branches, it's actually faster to just do them instead of making this crazy long equation. All right, valve emulation. We need xn. We need drive. We need the threshold. We need this PDF. You can just find it. You can just search for it. The book you have to buy, but this addendum you can find the PDF for it online for free. Thresh. We also need variable DC offset, which if I remember isn't actually really used, but I'm going to put it in there anyway. And then we need clip positive and clip negative. Okay. All right, that's our variables, our inputs. All right, start, simple. All right, these first two. So that is the offset. And I guess we don't need it to be const. And let's make this a float. Okay. Yep, okay. I'm going to do the skeleton of the if first. That one's threshold. Yeah, okay, so if is greater than thresh, we do something. Else if, what was that one again? Greater than 0. And then else, what was the else? Just a bunch of stuff. All right, so let's see. So, yeah, we got a nested if statement here. So in the first one, if xn is greater than the clip positive, we do something. Else, we do something else. Oh, this one's easy. All right. So yn is equal to that. Clip positive And this one, cool, okay. This one uses, there is a page with a table of a bunch of different wave shapers, and the Araya is the first one, and it works really well for any kind of like soft squared off shape. All right, we don't need comments. This is just called thresh. Now this is, let's see, positive, positive, thresh, thresh, thresh. And then whenever you copy and paste from a PDF, it does this cool thing where the dashes aren't actually a minus sign. Okay. Now this is ugly. I'm going to fix this. Okay, YN. Oh, we just need these to be floats. And we will get rid of that little warning. Nice, nice. Okay. All right. And then in this positive part, we just do YN equal to XN. And then the bottom portion uses a different wave shaper. So it's going to be similar to this, except for the negative, right? So if it's XN less than clip, clip negative, YN, yep, YN equal to clip negative, else the other wave shaper, just a tan, pretty simple. Okay, clip negative. And I like curly braces in all my if statements, even if it's one line. Clean this up a little bit. Okay, that should be good. And then we return YN, which is our wave-shaped signal. Okay, and we're good. Now, the only other thing that's absolutely necessary for the shape to be correct is the DC filters. So let's do that. All right, we're going to have an array of Linkwitz-Riley filters because they're just so simple to set up and use. Linkwitz-Riley filter float. And we got 2 of them for 2 channels. M DC filters. How about that? Let's go up here and set them up and prepare for auto filter in those. We're going to say filter.prepare, of course. Always need to do that first. We need to set the type. Linkwitz-Riley filter type, and these are going to be high passes. And we're going to set the cutoff. 10 hertz ought to be good. Okay. All right. Okay. Let's take a look at the signal flow just to make sure we're going to do it correctly. We've got our drive, then the conduction, then the offset, which we don't actually even really need, and then the valve emulation, then the DC. Yeah, that's good. Okay. So we are going to do XN is equal to, let's see here. I want drive to not be any larger than 30 maybe. So let's do times 0.3. And that'll be 0 to 30 instead of 0 to 100. All right. So let's do this. Const float drive is equal to that get next value. All right. So we're going to say not const xn times equal our drive to actually drive it. Then we're going to say xn is equal to, I already forgot what it's called, process conduction. Okay, there we go. All right. So the thresh he gives values for. Let's see here. Pretty sure it was like 1.5. And that, what does that do? Where is it at? Oh yeah, it's just the threshold for the compression. Yeah, that makes sense. All right, so that's 1.5, and then we're gonna say xn is equal to process tube. Okay, so xn, we're already driving it, so I'm not gonna add saturation. So I'm just gonna pass in 1 for now. We can obviously do whatever we want with that, but I think it's good the way it is. Okay, we need, what's it called again? Oh yeah, that shift coefficient, which I'm pretty sure is just 1. Yep. And then we have the clip points for negative and positive, which he gives as 4 for positive and negative 1.5 for negative. And that lines up to some measurements he took in the voltage range. So it works pretty good for this case too. So just stick with it. Okay, and then we send it out, and that's it. Oh, wait, we got to do our DC filter, of course. Xn is equal to, what's it called? DC filters. Yeah. Channel. Process sample. Channel. Xn, our input. Okay. Let's get rid of this warning. We're going to say static cast to int channel. Cool. And that's what I love about a CLion is when there's a warning, it shows you, tells you exactly what you need to do. So much better than Xcode. All right, so I'm going to build this standalone real quick just to make sure it doesn't like crash. Oh, and then we got to actually put it in our process block. That's the other thing. Let's see, what's it called? Tube float m tube. That's good enough. Then we prepare it. Then process, and we just pass it the block, which is upsampled block, and num oversampled samples. Let's see. Too few. Expected 6, have 5. Oh, I must have missed one. In here. Thresh. Oh yeah, I did. Okay, so xn k, which I'm putting as 1, thresh, which needs to be 1.5, just like the other one, and then that offset. Okay, so that's the one we're missing. Strange that it gave me the error in the other file instead of this one. All right, I'm gonna build again, standalone, just to make sure it doesn't blow up. Because I definitely don't want to have to listen to that if it blows up in Logic. Okay, there we go. Should be good. Let's build it AU. Get this set up. My plugin folder, and then the project. Comment channel strip. Debug. Artifacts. AU. Looks like it's done. All right. That certainly doesn't look great. I blew it. All right, what did I do wrong? Let's see. DC filters channel. Let me just comment out these two because I assume the problem's in one of those. Don't you use the juice copy plugin? Juice copy plugin. I don't know what that is. Is it called something else? Oh, okay, so the problem's not in there. Oh. Yeah. That's what it was. Thanks for that. Good looking out. That would have taken probably 5 minutes to figure it out. In CMaker and the producer, you can set the build to copy the plugin to the path. Oh, no, I don't do that. There was a reason, and I forgot. I think it wasn't showing up, and for some reason, even though it was going to the right place, it wasn't actually. I couldn't actually choose it in Plugin Doctor or Logic or whatever. It might have just been something wrong with my path, but still broken. Did I actually wait? Did I hit build? Let's see. At the very least, that should be fine, right? Drive smoothers, drive, and we got drive, which is set target value, value times whatever. That should be fine. Wonder if I just didn't hit build and I thought I did. In fact, let me go put that in there and see if it. Copy plugin after build. True. And let's see. We might have to. Get rid of that and then reload. Those kill commands that sometimes you have to trigger. Yeah, that whole kill audio command thing. Yeah, I think a EQ probably would be good to move on to. It could be pretty simple and fast. Especially just do like a graphic EQ, like a 10 band, like the 560. when I implemented this tube earlier today, um, it sounded so good that I was like, oh, I got to do this one. All right, first build taking forever. I bet if my Mac wasn't 5 years old, this would be faster. Also, if I was doing this on my Linux machine, we'd be flying. All right. Let's see if it works without having to copy it ourselves. I can't think of anything specific yet, but if you want to create your own modules to put in there, um, I think another thing that I'll do is make some kind of color theme system, and we can figure out a way to set that like with some kind of XML file or something, and then maybe you know, you all could add color themes and stuff like that. Let's see. Before I go crazy, to oh yeah, okay, wait. Well, hold up. Process block. Yeah, the block and number samples. Um. Oh, I guess we should. Well, if this is what the problem is, we need to fix that because that shouldn't. Not setting the drive should be. Oh, our drive smoothers aren't initialized to a like first value. That's what it is. So doing this will probably fix it. What we'd probably have to do is drive smoother. I don't even, can we do it in the constructor? Nah, let's just do this. Let's just initialize it. Dot set current and target value to 1. Also to contribute, I forgot about this. You don't clone the repo like normal. You do a fork and then you do a pull request. It had been so long since I contributed to something else that I forgot. Ooh, looks fixed. Let's see what our shape looks like. What we got? What we got? Ooh, looking good. Let's see. Oh. Oh, did I did I not uncomment out stuff? Yeah, of course. And if you all could think of something to contribute, because I mean, this could turn into like a kind of like a Slate virtual mix rack thing, and then everybody could like add in their own modules or something. Ooh, there we go. This is looking correct. Okay, there we go. We got that little bit of sway in the bottom, and then we've got our DC filter. Yep. Okay, let's see. Think we're gonna be good. Let's see. Yep, and we got that slight bump. Yeah, there we go. Oh, that's kind of weird looking right there, though. That shouldn't be happening. Oh, yeah, I think what we need to do, let's we got to scale it back while we're driving it. So um we could just do xn times 1 divided by drive, which isn't you know, a super efficient way, but if that fixes it, let's implement that a little bit better. That way, as we turn the drive up, the overall volume will come down equal to the drive. But it looks like the plugin copy step is working, so maybe I'm just stupid. Yeah, there we go. Oh, but it's still happening. Okay, I thought that there's some kind of threshold happening right here, and I think maybe that could be a mistake in the code because I don't remember that being a thing. So let's just go over it real quick. Let's start with the actual methods, and then we'll look at the a larger view. All right, xn greater than 0. Delta yn. Yep. Clip delta max. Compression factor. Compression term times exp. Return. Looks good to me. All right, this one's kind of looking like yn isn't being used, but that's not true because I see it right here. All right, let's see. Xn plus equal the offset. Then we got yn. Then we got if xn greater than the threshold. Yep. And then if greater than clip point positive, we are clip point positive. And then else minus equal that thresh. Greater than 1. Oh, wait. Else. Oh, okay. So this is supposed to be in an if statement. I missed that. If, what was it? Xn, or if the clip point positive is greater than 1. Then we do this. While we're here, let's keep going. Then the array thing. Yep. Clip positive minus threshold, and then plus equals okay. And then yep. All right, and then clip point negative equal to clip point negative, else if clip point negative. Oh, I must have missed this also. And let's see here. That should be it. Okay, let me look at this real quick. So we do our drive, conduction, tube, DC filters. That should be good. All right. There we go. Cool. Okay. Very good. Very good. I really like the small little inconsistencies in the shape, because if we were to do a regular like soft clipper, this would be like a perfectly rounded top going into a perfectly rounded top with the same exact values and shape and everything. But we've got these little inconsistencies like right here, and right here. And that, I think, adds to the realism. So let's play it in Logic real quick. Make sure I don't blow your ears out. All right, recent, I got a stream, yeah. And then this has a lowered gain. Let's see, is that coming through? Looks like it. All right. Let's see here. View toward DSP, the comet strip. All right. Looks like we had a little DC pop in the beginning. Whoa, that doesn't sound as good as when I tested it earlier. Something is awry. It's got to be a DC thing because I heard the little click and I feel like we shouldn't have that. Classic me. I test it out before the stream, do it perfectly, and then on the stream, doesn't work. XN drive, conduction, process tube. Okay. We already went through this, and that was all correct. Let's see. Is there something that I left out? I didn't implement this, but I also didn't do it earlier, and it was great. I didn't do the low shelf. The upper band filter doesn't make a difference. I don't think we actually need to flip the phase, and that's definitely not going to do anything for the DC or whatever it was. We did set our filters, right? Yeah, high pass at 10 hertz. Let's see, positive then negative, and that's in the correct spots, right? Yep, positive, negative. XN, drive, thresh, offset. What happens if the offset is 0? But I'm fairly certain that's not the way I had it earlier. This doesn't look quite right. Let me grab my laptop real quick and just check to see what I did earlier. Because there might be a difference. Oh, I mean, how about these filters? What did I set them to? I set the DC filter cutoffs to 5 instead of 10. That might make a difference. I also set the drive to 2. And then I've got the shift at 1. And that's really the only difference. Mm-hmm. I suppose I could take a look. Let me look at the code real quick and see if it's the same. Plus offset. Why? More than thresh. More than positive. Click positive. Else. That. That. Oh, well, I also didn't. I had the same mistake in mine right here. Let's try it out. We did change the, what's it called? DC filter cutoff. So let's try it and see if that fixes it. I thought header files only contain the signatures of functions and actually, so that had the implementation. Yeah, if you, so code that's in the header has a better chance of being optimized more. So most people put their DSP implementation in the header file. And since this is so small, I've just put everything in the header file. If this was a larger class, I probably would break out some other stuff to it, but I don't know. Works out for me. That does look a little better. Yeah, that looks a little better. Let me also put this mistake back in. Looks about the same. Okay, let's listen to this one in Logic, and then maybe we'll uncomment this part and listen to it again. We still got that pop. I think that's better. Let's put that back in. And then I guess I will do the low pass filter because that will probably help smooth it out a bit. I mean, maybe I'm stupid. That could be the whole thing that I'm missing. That I think thought was important, but actually difference. That actually seems better because as we get halfway through, I feel like there's more compression. All right, let's put that little high frequency. Okay, I'm gonna leave this the way it is. Let's do the Miller cap, which was it's some kind of capacitor that does a low pass at 10,000 hertz. So sure, I'm just gonna call it the Miller cap filter. Not that I actually know what that is, but he did. Because he's a genius. I'm just going to copy and paste this. Filter. Miller cap filter. This is going to be a low pass. And this is going to be at 10K. And then we do same thing. Miller cat filter. All right, let's try that. You know, I was kind of considering that the one divided by drive could be an issue. We can take a look at that and make sure, because that isn't the way I did it in the other one. So that should have been another red flag that could have been thing. So let's see. Let's go listen to it real quick. Okay, I mean, it sounds good. So let's doing this. Let's make another of these, and we'll say M drive comp smoothers, and we'll take these, and that'll be M drive comp smoothers, and then these will be what? We're gonna go in here and do the same thing basically. So drive comp smoothers, but instead of passing in the same exact thing, we just need to make this negative, and that way each decibel value will be negative, which is going to be bringing it down, so that should be good. And then we are going to go up here and say const float drive comp. I'm just going to do xn multiplied by that drive comp. All right, let's see if that makes a difference. Let's look at it in Plugin Doctor real quick. I don't know. It still looks a little different. Yeah, it still looks a little strange. I mean, it's fine. It's just let's just see what it sounds like. That pop is still there. I mean, it still sounds great. No, I don't know why he puts the cap after. Putting it after will bring the high end down no matter what. Usually you would put it before so that less high end frequencies are distorted, and the actual distortion brings more high frequencies in, so it kind of cleans that up. Because this making it darker at like 10,000 hertz, I think only really makes sense musically for like a guitar signal going into an amp. But if you want to use this as like a console kind of thing or something, it might not make sense. Let's I'm gonna put it before the tube and just see what it sounds like, because that's what I'm pretty sure that's what a tube screamer does. I could be wrong, but I think that low pass filter happens before the diode clipper. I could be thinking of a different unit or something. Okay, so it's not as dark now. I think, at least. Let's look at it in Plugin Doctor. Oh, it's still pretty much, yeah, it's still pretty much locked off. Oh, I guess it really doesn't bring any more high end. I'm surprised. Oh, I guess maybe a little bit at the top. But it seems like it doesn't make a huge difference. I'm just going to put it back. Let's also check if the compression kind of looks similar to his graph. He put it right here. Where is it? That's the power law. Here it is. Let's see. Load it up. Let's go to dynamics. That's kind of odd looking. Let me give it a little bit of drive. Okay, that looks more realistic. I guess that was just kind of hidden behind the edge. Does that kind of match? You know, maybe it does. Because I don't know if my eyes are playing tricks on me, but I think there's a little bit of a inconsistency right here. And if we look at plugin doctor, it's kind of the same thing maybe right here. And then kind of gets lopped off. So I think we might be good. The other thing we can do is we can check the performance. And this is a debug build, so it's not the best way to check. But looks like it takes about 6 milliseconds for our process block to run. And we can do one small optimization here. We can get rid of this if statement. And we can do same thing we did. YouTube, right? Hit the nail on the head with this stream for once. Can't stay and watch, but you just got a sub. Oh, thanks a lot. I think I'm gonna try to stream on Mondays, Wednesdays, and Fridays, so you can catch me any of those days. Let's see what we do in mask. So we do a mask pattern. Let's see, const float, or it's gonna give us a warning. We'll do auto. We'll call it mask is equal to static cast to float, and that is xn greater than 0. We could do greater than equal to 0. I think probably be fine. And then now what we could do is we could have all we need to do, we'll take this code out. What's wrong with that? Oh, yeah. So we have this mask, and we know that if it's positive, we do this, and if not, we do this. So we can actually just use the mix kind of logic. So if we do 1 minus mask times our dry, which would be not really our dry, it's the thing we want when our mask is negative, which I think is xn. And then we add the thing that we want when the mask is positive, which is this. And I think that's good. Yeah. And mask is only ever going to be 0 or 1, so we don't have to worry about an actual like mix, like in between values or anything. So that's a tiny little optimization. Now I did it for this entire block earlier, and it actually made it slower because there was so much more math going on, because there's like 4 or the 6 if statements that you have to mask for. So yeah. All right. Let's just make sure this actually works. Make sure I didn't do it backwards. Man, I can't get over how it's just a little different. And I'm sure once the stream ends, I'm going to realize what it is. But that's the way it goes. Still seems fine. Okay. All right. What about this little thing? I ended up, I know we already did this, but I already forgot if this made a difference or not. We do have 2 of everything, right? Yeah. Yeah. Okay. Oh, you know what? Maybe it really is the low shelf. Let me look real quick. I don't remember if it's actually in there or not. No, it's not. Okay. The only other thing I did was instead of let's see. Instead of having it clip the input like this, I did a mix. So yeah, let's do this. We're gonna make another smooth value and just call it mix. Give it the same name, mix smoothers. And what's convenient is our drive is coming in 0 to 100. So we can easily scale that down to 0 to 1 for our mix logic. This is just going to be set target value times 0.01 to get it to 0 to 1. And then we just grab that, put it up here. Get next value. Then we do our mix logic. But we need to change this up a little bit because we're altering our input. So let's keep the input clean by doing a another variable to hold our output. So we'll just do yn is equal to that, and it doesn't need to be const because we need to change it. So x in times, and then we can get rid of that, and then we could do this. And then we could do yn times equal drive comp. And then we'll say, we'll do another mix logic, and we'll do 1 minus mix. And then you put your dry after this one, which is x in, and then add in your wet signal and do that times mix. Only annoying thing is the filter is going to be mixed with the output. I wonder if maybe that was giving that kind of like phase imperfection. Maybe it was giving it a cool sound. I don't know. So basically what's happening is when our drive is 0, we're going to have no distortion. And then when our drive is all the way up, we're going to have all the way the signal. So a little bit more of a mix, a little more subtle. We actually might not even need that drive comp anymore. Nothing, it's dry. Okay. Yeah, that looks a little better. And we don't need the drive comp, I think. So let's get rid of that. Build it again real quick. Ah. Okay, this actually looks more like what I got. So I think we still do need the drive comp. We just need it to be way less. So what we could do is just go back in here, and to give us less compensation, we just make this number smaller. We could probably do 1.5, and then okay, yeah, we'll just see if that's good enough. Okay, let's take a listen to that. That looks much closer to what I was expecting. Still understand why there's a DC pop, but and it's dry, so our signal's not even in. So I don't know. We do get a little bit of that weird phasey issue because we're mixing with the filter. So I think we could probably let's do this. Const, or not const, let's just do float x in mix is equal to this. And then we'll say this. So now we're going to filter the entire output instead of mixing a filtered and unfiltered. And the only bad thing with that is when the signal's dry, it's still going to be filtered. But something we might want to do anyway is have the effect be on even whenever it's supposedly all the way dry. So we could do yeah, so we'll take this mix and we'll do mix is equal to juice, and we'll just map it to another range. It's from 0 to 1 right now, so we'll type in 0 to 1, and then we'll do like 0.05 to 1. That way there will always be, even whenever it's not on, there's a little bit of a you know, jump in harmonics and stuff. Okay, let's see. This is C++. See, we got a little bit of harmonics in there. And I do want to do some more like C++ focused stuff, not like audio. We could get some more, you know, reach that way. I'm sure people are always looking for help with C++ anyway. Not that I'm a savant, but you know, been doing it for a little while now. Cool, cool. Okay, that's all the same. All right, I guess we're good on that. That's the tube. All right, let's see here. All right. Git add. Okay, that's fine, I guess. This is going to be I recommend everybody learn C++. The world still runs on C++, so after Python, yeah, learn C++. Because you can use Juice to do, you can make desktop apps like desktop GUI apps or desktop audio apps, and then you can do audio plugins and stuff, and you can use Juice to make console applications. So I mean, you can really do a lot. And then there are obviously other C++ libraries. You know, there's Raylib for games. So it's just a library, no like editor or anything, but that's really cool and fun. There's also other GUI frameworks like what's the big one? Qt. So a lot of jobs will have that listed. And I'm sure there are way more libraries than that. Let me write this commit message. What did I do? Add to DSP and rearrange folder. The syntax will make your head hurt less after you do it for a long time. There's really no getting around it. I guess, and after learning something else first, it's probably harder. I learned C++ first, so yeah. Get pushed straight to main. Boom. All right, what else can we do? Could try to do the yeah, we have time for the EQ. Let's do a 560 inspired EQ. So let me show you the one I'm thinking about. It's the API 560, right? Yes. That is not a picture. Okay, great. I kind of wanted the actual. I don't want a plugin. I kind of wanted to see the hardware. Yeah. Okay. Just look at this. So it's just a 10-band EQ. Your only controls are the gain. So you've got 31 hertz, 63, 125, 250, 500, 1000, 2000, 4000, 8000, 16,000, and then the Q values are proportional. So as you pull down the gain and you're on just barely above zero, above or below zero, the Q will be wide, and then as you pull it up or down further, it gets narrower and narrower, which is not hard to do in code at all. Yeah, so let's do that. We need to make another I guess this would be a module. So let's do C++ header file, and we'll just call it graphic EQ. Pragma once. Just wrote a real-time zero shot ML library for audio and C++ at my startup. That's great. That's way cooler than anything I've ever done. So, so good job. Process block. Let's go get that. Graphic EQ. All right, so we can copy paste this more or less. graphic EQ. Oh, well, yeah. Let's do that. Let's see. Graphic EQ. We will have, I think, only one set of smoothers, so let's get rid of all this. We also I don't think we need to use a block loop. We'll be able to do this with, yeah, we'll be able to do this with just the block. We don't need the loop. Okay. And then we're going to have, instead of set drive, this is going to be, set gain. We'll have to come up with a smart way to do that. Let's leave these drive smoothers in. And that. Okay, cool. Let's go into process block and just set that up. What is this called? Oh yeah, graphic EQ. This is going to be called M graphic EQ, sure. Code a lot of Python at my day job. What kind of stuff do you do besides that ML library that you made? Dot process block, sure. Sample block. That's probably all we need. Okay, so graphic EQ in. All right, so all we need is 10 filters, 10 like band shelves, and man, I think I forgot how to do the processor duplicator thing. Let me go look at the documentation real quick. See if I can figure it out, or if I have to ask ChatGPT. Processor duplicator. Think we just, so processor type and then the state type. So duplicator, mono processor type, then the state type. So is that, so this would be like the filter, and is this the coefficients? I kind of forgot. That's okay. ChatGPT. Let's see. With juice IR filter, make notch. Oh, PhD candidate in automatic speech recognition for speech impaired people. Oh, that's awesome. Congratulations on getting that far. I hope you do good in your defense and your dissertation. Yeah, okay, I was right. It's the filter, then the coefficients. So we do this using, and why does it look so, why is it like that? Go back over there. So we need to make 10 of these. I think we could put them in an array. I don't see why that wouldn't be okay. Notch filter, 10 M filters. Oh, okay, cool. Yeah, I probably just don't recognize the screen name. Screen name. I'm so old. Okay, so we got 10 of those. Then So to make this real simple, let's just put the process code right here. So we're gonna do audio block. So I think we can just do for auto filter in filter. Oh wait, I forgot what I called it. M something. M filters, and then we'll just say filter dot process, and we'll do juice DSP process context replacing, and we just pass it the block, and that's it for the process. We do have to prepare them. Okay, cool. I'll keep out for that. I'll keep a lookout for that name. Filter prepare. Nope, that's process. Spec. And then we need to set the gains. So let's do set filter gain, and we need to do value, and we also need an index, I guess, constant index, and then well, actually, yeah, sure, let's do it. Okay, let's do it like this. Okay. I'm just, as I type, seeing more annoying things that are gonna pop up. So to use the filter, we let's just get out of this and let's just pretend we're updating a filter. What we would do is say like so it'd be m filters dot state. Oh no, sorry, m filters the index, and then do dot state, and then you do is equal to juice coefficients, IR coefficients. Where is it at? Right there. Yeah. So juice DSP IR coefficients. I guess we do float, and then it'll be whichever one we want. So make low shelf or bandpass or whatever. And these are going to be notch filters. So the sample rate and the frequency, no, peak filter, sorry, because we want to be able to set the gain factor. Okay. Okay, so we need the sample rate. So let's do, yeah, float m sample rate 44,100 by default. And then we will do this, set it to our actual sample rate, spec.sample rate, and then we can pass this in to the sample rate. What's your problem with this? Doubled float. Oh, okay. This is coming in as a double. Okay, so we'll just static cast the float. Cool. All right, so what's the other? We got sample rate, the center frequency. So if we pretend this is the first one, we're just going to type in 31. Then the other thing is the Q, which we're going to have to come up with a way to set the Q proportionally. That, and then a gain factor, so like 3 or whatever. So, okay, cool. Yeah. So this is how you update the filter. So you need to do this before you call process. So we got 10 of them. What's the best way we could do this? I'm thinking that we can, in the update method, we could call, m graphic EQ dot set gains, and we can just have like a vector of 10 values that we set before and then pass to the module. So we could do like set filter gains, and then this would be const std vector of type float, I guess, and then I guess by reference, and then we'll say values, and then then okay, we'll do that. Int I equals 0, I less than I guess values dot size plus I. Oh, I think we're gonna need to do the gain and the Q in the same method. So I think I'm gonna set filter parameters, and then we're gonna call this gain values. I think we only need one still, so let's just do that. So we need to do, oh, we need to do this. Okay, so filter, and then 1, and then yeah, gain values. So is that in gain? I think that's in decibels. So decibels again. So that right. Okay. Okay. So this app is an audio plugin, and we've done some distortion already, and now I'm making an EQ. And yeah, we should be able to use this for anything. We're making a channel strip plugin, so you could use that in a DAW, but you could also use it in your streaming software if you do a USB mic like this Elgato one when you're playing games or something, and then you could also load that onto your mic to do some processing. Let's see, we need our cutoff value, so let's just do std vector of floats m cutoffs, and I think I could probably just do this, right? 31.0, then 63, 125, 250, 500. And then we'll do this. So there's our cutoffs. And why is it not? There we go. That's better, I guess. All right, so that, okay, so now we got to do the Q. So so the real hardware 560 had a range, a dB range of -15 to 15. So let's use that. And what we could do for the what's called proportional Q, we could just well, actually, before we do that, let's just do it the way it is now and make sure that it's actually working, and then we'll do that. So that all seems fine. Just need to make sure. Let's see. Oh yeah, we need to go put these parameters in there. So there's probably a smart way we can add 10 of these without writing it 10 times, but you know, That's a problem for future me. Let's see, graphic 1. 2, 3, 4, 5, 6, 7, 8, 9, 10. Oh. I think this would be a good task for ChatGPT. Actually, yeah, let's do that. Let me let's see. Let me put all this stuff. That's not any better. Yeah, so far it's basically a driver, and now I'm doing an EQ. There's a better way to do this. I've done it before, so I'll go get that later. We're just gonna leave it the way it is now. Oh, 10. Okay, yep, that all looks correct. All right, so then we got to do that right here too, unfortunately. So this is gonna be graphic 1, 2, 3, 4, 5, 6, 7, 8, 9, 10. And then that's this one. Let's see, this. And then this graphic 1. Okay, and then we can do that 10 times. 2, 3, 4, 5, 6, 7, 8, 9, 10. Oh, I hate when it does that. I gotta click away from it every time because it's trying to autocomplete. Almost done. Okay, then we gotta go to our processor and actually put those in. So that's this. Two, 3, 4, 5, 6, 7. Oh, wait. Let me at least do this. Graphic 1 ID and then graphic 1 name and then this -15 to 15. Then copy paste it. 2, 3, 4, 5, 6, 7, 8, 9, 10. I know this is probably mind-numbing to watch, but I guess this is the reality of software development. And then one more place, we got to do it. Wait, do we not need the listeners? Because I didn't implement them. Oh, I guess we don't need it. I don't know if I've ever noticed that before. All right. So we need to do an std vector of floats. We'll call that cutoffs. And can we do it like this? Can we do parameters dot graphic one param dot get 3, 4, 5, 6, 7, 8, 9, 10. Okay, and then we would do m graphic eq dot set filter parameters, and we give it those cutoffs. Oh wait, it's not cutoffs, it's gains. Okay, I think that's it. We should be able to run it and see if it actually does anything. That looks correct. There's definitely some things we need to guard against, like if gain values and cutoffs and filters don't match the size. Let's see. So yeah, let's just do that. We could just do jassert false. Oh wait, just do jassert gains. Oh wait, sorry. Gain values dot size and m cutoffs. Wait, why is it not auto completing? Oh, so yeah, sorry. Size is equal to m cutoffs. Why is that not? Oh. Okay, and then I guess we'll do one more, and we'll just do filters right here. I think that's probably good. And then if that does happen, we should be able to see it in the console. So actually, yeah, let's run it standalone. See if we see that warning, and if we don't, then I think we're good. Oh. Oh yeah, I didn't pass num over samples. I don't think it really matters, but we could probably go take that out. I'll leave it in for now. Not bad to have in case we need it. You never know what you're gonna add to that class. Oh, got a crash. Let's see. Run it in debug. What we got going on? Bad access. Let's see. Graphic 1 and 1. Okay, so maybe. Did I miss? Yes, I did. So 10, 9, 7, 6, 5, 4, 3, 2. Okay, so are these good? 1 through, yeah, okay. Let's do it again. Oh, I hear a train. Okay, cool. Looks like they're good. All right. Let's build that and see if we got an EQ. Okay, looks like it built. Let's see. Mm-hmm. Uh-oh. That's not great. Let's see. I'm sure I broke something. So we're calling that. Mm-hmm. And this is happening before process. No, it's not. Yes, it is. Because in the processor, we've got update parameters. And inside of update parameters, we've got update parameters, which is this one. So, filter gains. Okay. Let's go into the graphic EQ and see if maybe we're not getting what we expect. Yeah, I guess we'll do debug and then let's see. Gain for I, and then that, and then that. Okay, let's see. Okay. Looks like they're coming in correctly. Is it maybe a initialization issue? Like, what if I set all the values to something? No, probably not. Okay. Let's see. I'm pretty sure they need to be in gain. Decibel gain value. Okay. I wonder. Okay, we're saying prepare. That should be fine. Process. I wonder if no, it's not a const block, so that should be good. Oh, actually, okay, so that's just buffer. And then block. What if I do this? Put it right there. Get rid of that. Oh. And then we'll do this. Gains, and we'll make all of them like 3. and not actually change them in real time and see if that makes a difference. So let's see. Yeah, gains and then gains. Okay, filter state, yeah. Okay. Oh. Well, I wonder, did I forget to switch back to AU? I don't know. A lot of times I will forget that I'm still on standalone and I'll hit build a bunch of times and not see any change in plugin doctor, and I'm like, what's going on? Nah, still don't work. I wonder. Shouldn't it give me an error if that was necessary? Okay, that's what it was. We don't need this. That should be good. Let's see. Oh, look at that. We got an EQ. And what we want is for the Q to be wide like that. And then as we get larger or smaller, it should get narrower. So we could do that pretty easily. So we could say I mean, we could really do it in a bunch of different ways, but I'll just do const Q is equal to, well, I'm not sure. Let's do this. Const we know our gain's coming in 15, so we could do const gain is equal to std absolute of gain values. So that'll be 0 to 15 no matter what it is. So constant gain. So that's 0 to 15. We know that. So that means oh, actually, let's make that 0 to 1. So sorry, I'm stupid. I gotta do a calculator. What's 1 divided by 15? Okay, 0.6. Let's just do 0.66. So that's 0 to 1. So if it's 0, we could just do a map. So we could do const float q is equal to j map. We're going to take gain, which is 0 to 1. Oh, sorry. J map gain, which is 0 to 1, to 0.3 maybe. Let's do 0.5 to 0.95. Okay. Oh, that. Okay. I think that's it. So Whether it's positive or negative, we're going to get 0 to 1. So 0 should be the widest, 1 should be the narrowest. Okay. Let's see if that works. Honestly, I can't tell. It kind of seems like it's not working. So let's see. Debug Q They should all say 0.5. Okay. And let's pull them all down. Okay. Oh, wait, the juice filters aren't 0 to 1 for the Qs. That's what it is. I don't remember. Let's see. It's juice. Let's see, juice filter or coefficients. Okay, let's look. Let's see if the documentation says oh wait, coefficients. No, actually make low pass. Let's see. Which one is it? The peak that we want? Great, it doesn't tell us. Okay, so let's just guess. I think it could go all the way to like 10. So let's put 707 back as the default. And then, I don't know, maybe we'll do 9.5. Okay, it's working now. Let's see, let's take one in the middle. Take that one. Let's see, it doesn't stay very wide for long. I mean, I guess that's okay. All right. The other thing we could do is use a decibel scaling, I guess. So, what is 15 dB? 10 raised to 15 divided by 20. 5.6. Okay. What about 25? Or actually, it's 30. Yeah, okay. All of a sudden, it doesn't know that I'm trying to calculate something. 10 raised to 30 divided by 20. Calculate. 31. Okay, that's way too high. What about 20? That's 10. Okay, we can do that. All right, so I think what we'll want to do is take gain. Sorry, I'm confusing myself. Let's see. Yeah, let's just take this. So it's 0 to 15, so this will be decibels to gain. That will be, and then add 5. No. multiply by 1.5, I think, right? 15 times 1.5. Oh, this is a little too much. Okay. That's fine. Let's do that. Okay, so that's going to be 0 to whatever. So let's add 0.7. Oh, wait, no. Yeah, we just do this. Instead of the map, we just do this. Right? Because this is going to be 0 to, what was it, like 19. So this will be 0.7 to whatever. So, oh, wait, we don't want 18. We want 10. Right? What was 15 again? 5. Oh, no, I was right. 20 is 10. Okay, we're good. So that's 20-ish. Okay. Okay, yeah. I confused myself, but I think we're there now. So now our Q mapping is on the decibel scale, which should start slower and then speed up towards the end. Let's see. Yeah. Oh. Let's see. Let's debug what that is. Because maybe I'm wrong. Okay, what do we got? 1.7. Okay. Oh, I'm getting 0.8. Ooh, that's weird. Let's see. I did something weird. Let's see. The absolute value of. Oh, wait. Is it because of this? So the absolute value. Okay, so decibels the gain. That's 0 to. No, we want that because that's 0 to 20. So is that not 0 to 10? Or I'm sorry, 1 to 10? Oh, I'm doing something wrong. My logic is off. Why is that? So dB to gain. Maybe it's because of this. The absolute value of that should be 0 to 20. Okay, 8.6. That's good, I guess. So this is actually needs to be minus 303, right? Or no, sorry, 293. It doesn't really make a difference. So let's do that, and that could be a little higher. So let's do that, and I think we're good. So let's see if that let's see if that decibel scaling actually makes a difference. And then if that's all good, we made an EQ in less than we made an analog inspired EQ in less than an hour. Yeah, there you go. That's better. So you can see it starts off pretty wide, and as we increase, it gets really thin, which is what you would want if you have that much reduction. And the same thing should be true at the top. Yeah, okay. Cool. There you go. Made an EQ in an hour. And it's oversampled. Not that it needs to be. Let's see what difference it makes. Oh, yeah, I guess we gotta account for the oversampling. Or, I mean, you don't need to oversample EQs anyway, so we could just not put that in the oversample loop. All right, cool. There we go. Git status. Git push. Okay. Well, I think that'll about do it. Thanks for watching. So I guess I'm gonna make 2 edited videos after off of this stream. So I'll have that coming in the next few days, week or so. So yeah, cool. All right. Thanks for watching. I will see y'all next time. Feel free to join the Discord. The link for it is in the past video that I uploaded, and I'll put it in this one too. So in a few minutes, if you go to this video on my channel, you should be able to see the oh no, it's already there because I put it in OBS. So yeah. All right, cool. I will see y'all next time. Wait, maybe it's just me, but GPU code of any kind is the only code that annoys me. I haven't done any of the GPU audio stuff, so I have no idea. Yeah. Yep. Just getting back. I'm finished. We did a EQ analog inspired with a proportional Q. Did that in about, I guess, 45 minutes. So yeah. I'll be in Discord if y'all want to chat. So cool. Peace.